I'll go ahead and announce the next speaker, John Barr. And as you can infer from my talk, he's going to be talking about infrastructure-related things. He works on the ACES upper stage and advanced programs at United Launch Alliance. And some of his other earlier experience included the Delta IV upper stage and things like that. So without leaving more time for the talk, I'm going to go ahead and turn it over to you.
Thank you guys. Really appreciate you guys having me here. It's fun to be with the interstellar crowd. As you can imagine, I'm just a rocket guy, right? So some places that carries a lot of weight, but around here I'm like, it's kind of mundane. But anyway, much of you guys I think I saw from the tour a couple days ago, and so I'm glad you guys got to see the hardware out there, and so that was a fun activity as well. So I'm going to talk a little bit about rockets, and then and really leading into CisLunar, and as you kind of heard, where does this all tie in? And it's really that the space commercialization is a key stepping stone to get to the ambitions you guys have to go interstellar. And so there's some really important synergies and of that, and so that's really where this talk is headed. So if we can, I get to control this actually.
Launch Director. LD's ready. Stand engineer, proceed with MLP transport to pad.
Roger.
ULA is the world's most prolific space launch provider. We are America's ride to space.
From launching Mercury astronauts, to delivering every operational GPS satellite, to sending every U.S. mission to Mars, America's call to space for nearly 60 years. As a new era dawns, ULA continues to set the pace.
The next couple of years for ULA are very exciting. There's a whole host of things that are going to happen. First, we're going to return to flying Americans to space from American soil.
Scheduled for flight in 2018, ULA's Atlas V rocket will launch Boeing's Starliner on missions to the International Space Station. With the crew access tower nearly complete at Cape Canaveral's Space Launch Complex 41, production and tests will begin this year.
Every mission we launch at ULA is vitally important, whether it's reconnaissance or communications, weather forecasting, NASA science. All of these things enable life as we know it today. What we're doing with Commercial Crew in the Starliner program is taking that heritage and those principles and applying them to the systems that are going to keep humans safe.
We are very excited about the human spaceflight mission, but also we're going to introduce our new rocket, the Vulcan rocket.
Innovation is basically in our minds every single day. We're always thinking about the really great things about both our Atlas and Delta launch vehicles and kind of combining those things and our lessons learned to create this one really great launch vehicle with all of the good things that we have from our heritage vehicles.
Combining a 5.4-meter diameter payload fairing with a powerful American-made engine and up to 6 solid rocket boosters, the Vulcan Centaur will reliably and cost-effectively launch the full spectrum of mission types. With the introduction of the ACES, ULA will forever change the way we think about launch, on-orbit operations, and the possibility of space.
A reusable, very long-duration upper stage is going to allow us to create a fleet of space trucks, a true transportation system that will unlock the tremendous economic value in human potential that exists now just beyond our reach.
So anyway, that video is going to just really giving you a snapshot of where things are at. ULA has both the legacy Atlas rockets and the legacy Delta rockets. So we really have what I say is we have over a century of accumulated, launch legacy within ULA. So, we've been doing this a long time, and as ULA, after the formation of the joint venture of ULA, which is half owned by Boeing and half owned by Lockheed Martin, we've been plugging away with good success. We're at 121 right now, and there's another launch we have scheduled for tomorrow morning. They had to scrub from this morning to tomorrow, so we're plugging away on our tempo. This will be the kind of the last self-aggrandizing chart I do, though. So one thing that's happening is we are in the process of moving to a new launch vehicle. And this is really really is intended to take the best of Atlas and the best of Delta and bring those elements together into this new Vulcan rocket. We're looking to reduce cost. Simple really means lower cost. So we're looking to reduce cost. We're looking to have more capability, but an essential piece in all this is that we need to get off the Russian engine that we have today with the RD-180 engine on the Atlas for really political reasons. Congress has said you need to get off, and we're doing that. And so that's one of the key motivators behind the Vulcan. You see on the right there the ACES upper stage, which is a new, larger upper stage. It's built very much like the Centaur upper stage, which is a thin-walled stainless steel construction, monocoque construction upper stage, which has actually had the best mass fraction of a hydrogen-oxygen stage for like 50 years. It continues to have the best mass fraction of any stage, and this is essentially a scaled-up version of that, but with some other goodies going on as well. But so the other aspect of this is the ACES, and that's the part I've been working on historically here. So, and I apologize, when we fly, we will not put a deck of cards on the side of the rocket. It's really bad for the MLI, the boil-off goes up, so we can't do that. So, but the ACES upper stage is our new bigger upper stage, and there's a bunch of aspects to that. Being physically larger, right now the Centaur upper stage or the Delta equivalent of the upper stage are really undersized for the size of the boosters that they're on today's system, and certainly with the Vulcan they would be as well. And so there's a whole bunch of benefit we get to just by simply scaling up to a bigger size stage. And so one of the key features here is we're going to get a bigger stage that performs better. There are cost-saving aspects. We're trying to do this much bigger stage at a price point comparable to the small stages we fly today. And the third piece, and the part I kind of key on in this, and more my area, is there are a bunch of extra new capabilities that show up with this stage. We're talking about much longer durations, the ability to provide a whole lot of electrical power to payloads, and we open the door with some of those things into in-space refueling and reusability that way. So there's a bunch of aspects of that, and that we think really open things up, particularly for the CisLunar world. One of the key technologies hiding in here, and I'm sorry my pictures aren't quite as nice as I'd like, but is a thing called integrated vehicle fluids, IVF, not in vitro fertilization. But I wish they'd done the acronym better. But integrated vehicle fluids, and essentially what it is an APU, an auxiliary power unit. It's an internal combustion engine that burns hydrogen and oxygen out of the main tanks, makes a whole lot of electricity, and essentially in doing though, we eliminate our main vehicle batteries off the stage. So those are gone away. We have discharge-only batteries, and those are gone. It also, we basically take propellant out of the tank, heat it up, pump it up, and feed it back into the tank to autogenously pressurize. So we pressurize the hydrogen tank with hydrogen. And that gets rid of a whole slew of helium bottles we have festooning the back of our rockets. And with the bigger sized ACES stage, there would have been even more. So we essentially eliminated all the helium off the system. And the third aspect of that, we have little hydrogen-oxygen thrusters we use for attitude control that are very high ISP and actually the greenest propellant out there. That basically takes over the attitude control function, and we get rid of all the hydrazine and hydrazine ops off the vehicle. So we've done vast simplification. Along the way, though, some really important things are happening. And I'm sorry, with the pictures down here, you can see an engine block from one of the prototypes, and on the right-hand side, you can see one of the hydrogen-oxygen thrusters being tested. This is actually moving along and is actually fairly advanced. We have now tested the all-up IVF system, the engine, but it's like in your car, your engine has a water pump and an air conditioner and a bunch of other stuff festooned on there, and we do too. We end up with compressors and valves and heat exchangers and a bunch of other things incorporated in the system with the engine. So we're actually at the point where we've been testing at a full-scale prototype level of the all-up system and are headed off toward, for instance, running actual tank pressurization cycles on the ground out in the end of 2018. So this is actually moving along pretty briskly. Along the way, though, this opens up some really interesting possibilities. One is that our current mission duration... Closer to the microphone so we can hear you. Thank you. How long were you gesturing for? Just one. Okay. So one of the aspects of that is we can talk about much longer durations than we've had in the past. Right now, missions last on a matter of a couple hours, or a geo mission, maybe 8 hours, really short durations. But we've gotten rid of all our mission duration limitations off the system, in the sense that our batteries don't run out, and if the batteries didn't run out, we would have run out of attitude control duration, or not be able to relight the engine. We made all these things go away, so we're now in a position where we can talk about much longer durations. So as long as the propellant lasts in the tanks, we can keep doing, mission things. So there's some interesting aspects here. Another aspect of this is when you get rid of the hydrogen and the helium off the system, if you want to talk reusability or refueling of one of these stages, we've gotten rid of 2 of the 4 commodities out of there. And some things like helium, which sound simple, are actually really hard to transfer and it becomes a big pain. And so by getting down to just 2 commodities, the idea of refueling gets easier, and the idea of using in situ propellants from space, where there's an abundance of water in our solar system, and the ability to basically separate that and make hydrogen and oxygen out of that, we start opening up the options of in situ propellant utilization. So there's a whole lot of things that end up getting enabled by this very cool IVF system. One other aspect of in here is the ZEUS lander kit. And so essentially we just have a stage, and by adding, and that stage now can last for, now we can talk on the order of weeks. So for a trip to the moon, we can essentially fly off to the moon, keep propellants on board, do the lunar orbit insertion burn, do the deorbit burn, do a perigee burn, just to, as we come skimming in low over the surface, and bring ourselves essentially to a stop a mile above the surface, something like that. And essentially that's the point where the ZEUS kit takes over. We basically have hydrogen, oxygen, deeply throttled smaller thrusters that would essentially allow us to settle the stage down on its side. The IVF system that was there that has all this abundant power capability in there is still available to run that, so we can actually use electric pumps to go ahead and do that and set this thing down on the side. We obviously need guidance and control, and I mentioned the Cobalt system is something NASA has been developing that looks very applicable, and we need some legs, landing legs on there, but because we set the stage down on its side and the payload is really quite close proximity to the surface, they can be little stubby legs and very lightweight, and so this ends up being potentially a very lightweight system. So we really look at this as a kit on a stage rather than a whole new dedicated lander development. If you go back to a past NASA example, it's kind of old now, but Administrator Bolden referred to having a dedicated, I think it was the resurrected Altair lander. If they had brought that back, they throw out a number of many, many billions of dollars. As a kit, this gets a lot cheaper here. So when you step back and you go, I've got stages. I have stages I can reuse in space. I could refuel in space. I have a lander version of that. We feel like we're getting the infrastructure really needed in the CisLunar arena. And so we're feeling confident we have a good story there. So in concert with that, I'm going to give you a little history on this. A couple of years ago, we stepped back and said, gee, the launch market, because we look at this as a company. We make money, and that's our official objective and all this kind of stuff. So we stepped back and said, gee, the launch market out there is a very static thing. Really, there's a bunch of telecom satellites out there. There's some national security satellites out there. There's some NASA science satellites. But the marketplace has really been, in terms of the number of launches, very, very static through the decades. There really aren't that many more launches happening now than there were in the 1980s and 90s. And it really hasn't changed much. We stepped back to say, what could we do to kind of, is there a way there could be more market? And so we started looking at the commercialization of space. And so what you see on here is across at the bottom are different mission areas, and in blue you see existing markets. And then we started probing around to say, what are the emerging markets? What are some new future markets that could show up? And where is there opportunity? And this really kicked us off into this a discussion of the CisLunar world, and talking to lots of commercial entities out there to kind of explore where could all this go, and what does it take to bootstrap commercialization of space? Because really the government-only model really hasn't gotten us there over the ensuing decades. We haven't had the growth that you'd want to see. So what do we do to get there? And so we basically we hosted some forums with a bunch of people. We had mining guys, and there are people who want to mine asteroids and the South Pole lunar craters, and there's a bunch of different little entities out there. We ended up talking to almost 100 different companies or entities out there that participated in some of these workshops, and it was really exciting, really interesting to see the whole breadth of interest out there of people who have different pieces, parts, They want to do things in space, and you can see the promise of commercialization in space. Though we organize the first of these conferences, really we see ourselves as not the leaders of this, but really the cheerleaders of this. ULA is not, we're not going to be minors. We really just see maybe a niche for more launches, and we have some good pieces for the transportation infrastructure. And so we're really kind of looking at, is there a way, a lifting tide raises all boats. We just like to be one of those boats that goes along with that. So we've been trying to encourage this CisLunar arena. Let's go ahead and now try the other video and see if it makes it more.
The introduction of ULA's Vulcan Aces rocket, a self-sustaining economy beyond Earth is within reach. Space has long been an elusive place few people have experienced, let alone considered making it their home and livelihood. CisLunar, the space between the Earth and the Moon, though just a week away, is vast in the resources and opportunity it promises. Revenue is vital to unlocking the new industries that will form the backbone of an in-space economy, and commercial habitats are a first step for research and the manufacturing of goods such as pharmaceuticals and fiber optics. Production facilities in space will depend on the safe, reliable, and affordable delivery of crew atop ULA's Vulcan Aces. In the early stages, on-orbit manufacturing will rely on materials brought to space from Earth. As the economy grows, mining the lunar surface and eventually asteroids provides the raw materials. With the addition of a simple landing kit, ACES transforms into ZEUS, a transport vehicle capable of landing on and launching from the surface of the Moon. Years of science and exploration missions have proven vast amounts of water on the Moon, and with water, fuel can be made. On-orbit refueling enables the transport of materials and goods from low Earth to L1 orbit. Refueling also changes the paradigm on Earth. Large commercial satellites previously delivered to a transfer orbit can now be taken directly to geosynchronous orbit, enabling more satellite performance and capability. Looking farther into the future, resources harvested from space can be used to manufacture and assemble on-orbit solar farms, providing low-cost, clean power to Earth. With a thriving economy and reliable transportation, CisLunar is the first step in sustainable expansion beyond Earth.
Okay, I think you get the idea where we're headed in terms of a vibrant CisLunar economy and all the elements that could come into play here. So I'm going to touch on a few more points. So, we're out there exploring how to bootstrap space. If you have a vibrant commercial infrastructure out there, ECONOSPHERE, as we've called it, we end up with commodities from space. We end up with humans in space. We have construction in space. We're laying the groundwork that really that I think the interstellar world needs this infrastructure out there to make this all much more affordable. The CisLunar space can depend on fairly traditional business type paradigms in terms of having, justifying investment, making things happen. If we're interstellar, this is something that's a little different. You need a NASA or an entrepreneur or somebody or a philanthropist really to make that happen. But if we can make this space cheaper, we start, with these kind of elements, we start making it more affordable where something, for the $1 billion that a NASA could afford, you can start doing the things you guys are trying to do in here. So I think that this is a really strong, an important precursor step on the path to interstellar. And so, though we show this cute story out here of all these propulsion elements, as you saw, and I mean there are cool stories. That ZEUS lander, if you just launch it as a single launch, it takes 4 tons to the lunar surface, baby step. If you did that distributed launch, the refueling in low Earth orbit from Earth propellant, now you can carry 20 tons to space with essentially, or to the lunar surface with a dual launch. If you get to the point where you have an L1 propellant node out there, you then fill up that node, and you could haul 60 or maybe 70 tons of payload down to the lunar surface from L1, fly that same stage right back off the surface, back up to L1 and refuel it again, and be able to do that over and over again with that upstage, and you have a reusable stage for emplacing things on the moon. Once you have in situ propellants on the moon, you can flip that around, and you can fuel up that Zeus lander on the surface of the moon, haul 60 tons of propellant upstairs, fly yourself right back down and gas up, and keep doing that over and over again. And you can see how all that sort of bootstraps together. So chemical propulsion, which really isn't the avenue you guys are going to want to go to interstellar destinations. I look at it as an enabler. The hydrogen oxygen economy is an enabler of commercialization. Commercialization is an enabler for interstellar. I do have one chart in here where there is a curious angle where you could actually talk about chemical propulsion having direct benefit into your world, which is interesting. That's counterintuitive that we could ever develop the energies you guys need, but there is one cute angle there. And lastly in here, the space solar power, it's kind of the killer app for this space commercialization. It's the thing that could drive it all forward. If you develop lots of power in space, beam it to Earth, and then using that terrestrially, it's the engine that makes the solar power work, but it's the engine that drives a lot of this other commercialization forward more quickly. And so that's a really an enabler thing. And for you guys, that beamed solar power through lasers ends up maybe being the key technology you guys need too. And certainly yesterday we saw a lot of stuff talking about a lot of ground infrastructure to do that, and some limitations from trying to fire that many lasers off the ground. If space solar power infrastructure happens, the idea of space-based solar power to drive your probes, into the interstellar region really is a great opportunity. So there's an interesting synergy here where the thing that makes space commercialization happen can actually directly benefit you guys in the interstellar world. So the CisLunar, I'm going to give you a little bit of the idea of the CisLunar vision that came up in those workshops. CisLunar 1000 really is talking about having 1,000 people in space. So we have today down at the bottom where we're essentially a handful of people up there at space station. We have expendable launch vehicles. There's the kind of standard business you see of NASA research and imagery, telecom satellites, but it's kind of the world you know right now, and that gives you an idea what kind of dollar value we're talking about. In our minds, we have a vision that in 5 years, you start seeing the first steps of the commercialization occurring. Prospectors, lunar prospectors are out there. We talk about the new ACES stage, which then brings a bunch of capabilities with it that help drive this forward. Commercial space habitats are a real possibility. You have Bigelow out there, for instance, who is encouraging of potentially commercial space habitats, and you can see that starting. So you see the seeds starting to sprout there in the 5-year time horizon. Out at 15 years, you start seeing more and more elements. Prospecting turns to mining on the lunar surface. We have a Zeus lander showing up in this scenario, and refueling starts to show up. LEO tourism starts showing up, and so you can see the elements coming together. And then out for the 30-year time horizon, where we identify maybe 1,000 people in space, you see a much more fleshed out full vision of space commercialization happening here. So that's kind of the vision we're bringing forward. And when I say that, it's not ULA or the highway. It's really they're just trying to be cheerleaders for this whole community of small entrepreneurs mostly who are trying to bring this vision forward. I do want to throw one little plug in there for water. You saw it in the video a little bit, but they're finding water everywhere. There's water. They're finding water on the moon and water in the asteroids. On Mars, it's out there everywhere. We really see a hydrogen oxygen based architecture for all this transportation is really making a lot of sense in this CisLunar world. I recognize it's not the interstellar world. I mentioned the space solar power. It's the killer app. It uses all these resources, but it's the thing that makes commercialization happen, which you need. It also directly may be there for beam power for you guys. So it's a really key thing. Here's the one weird one I'm going to throw in here, and I'm not a trajectory guy. My trajectory guy swears these numbers are true, which is we may be able to do something pretty cool out into, not to other solar systems, but to get things into deep space quickly. There's some interesting scenarios here. So that this is actually, I think, derived off of the Pluto New Horizons trajectory down here. Pluto New Horizons trajectory down here. But essentially, if you go ahead and chemically, if you get 2 ACEs up to L1, both full of fuel, and so that could be some ACEs that got up there that got refueled, or it could be distributed launch, multiple launches getting them up there. But you start with 2 ACEs in an L1 depot. You basically do a Earth flyby maneuver and burn essentially one of those out as you do the swing by Earth, and you send this thing off toward Mars, and you have this ACES stage still there. And there's the thermal thing I'm going to get to in a minute. But you send the stage, it does basically a free return around Jupiter and plunges virtually straight back at the sun. So you're dropping virtually straight at the sun. You're just skimming by it. And if you can preserve the propellant in there, which means keeping your propellant alive for a 5-year transit and through a really hellacious environment as you approach the sun, kind of like the Solar Probe Plus is. But if you can keep that tank of propellant and you burn it as you swing by close by the sun, you can actually get to a C3 of over 10,000 chemically. And so if you guys want to go out and lens off of the sun or put something into deep space to kind of understand the environment there, this still isn't going to get you to another solar system, but it's interesting that chemical has the potential to maybe help out with some of the precursor missions, which is, for me, very counterintuitive. I never would have thought we could really get to the energies that were really needed for that, but C3 at 10,000 is a spectacular number. So I just want to that's my one little teaser. Maybe chemical has even a place for interstellar. And so just as my getting off the chart, off the stage chart, we are out there trying to encourage this CisLunar econosphere, CisLunar economy. We think our propulsion technology suite really can lead toward good transportation for that. And even though chemical isn't going to be used directly for getting all the way to other solar systems, we feel like the chemical propulsion is really an important step for this CisLunar economy. The CisLunar economy, with people in space, using resources in space, manufacturing in space, is really going to be an enabler for the interstellar world. And so, we think there's a direct tie-in here. All right, thank you. Justin.
Let me make a historical note. The SSP, so Space Solar Power Program of 15 to 20 years ago, did have an intention, a subtask, to look at driving beam-driven sails into interstellar using space solar power. And that was actually the reason why we did those launch experiments I showed you yesterday. So that's an idea that's been percolating for some time, and let's hope someday it comes true.
Thank you. All right, another question? Anybody?
Yes. So on ACES, is ULA currently planning to continue to use the RL10? And if so, how do you plan on keeping costs down, like you said, to about the same?
So and it gets more layers in here. The ACES stage, there's a bunch of technologies we want to introduce in here, and we also want to realize all the cost savings we can. There's always the tension of get it fielded quickly versus get all the thingies you want in there. So there is actually what makes it in on the very first version, what shows up as a block upgrade 3 or 4 years later, is certainly something in the middle of trade space right now. So the very first ACES upper stage you see out there may not have all the bells and whistles on it. It may end up lagging behind a few years.
And did you plan on incorporating active cooling systems? Would those, for instance, the longer duration missions like the Jupiter flyby that you proposed?
So the Jupiter flyby is certainly the most strenuous mission scenario we've talked about. A 5-year duration. We are working, essentially today's stage is hours. With the ACES stage that we described up here, we're basically getting into weeks. When I pointed to distributed launch there. You saw it flash by briefly. We end up with a tanker that really needs to hold propellant, not for a couple of weeks, really a month to make sure you can get 2 launches off together. And we are doing things to look at about trying to get into the multi-year domain as well. When you talk about 5 years and then also surviving as you plunge into the Solar Pro Plus is, you have to have really spectacular, sun shields and things like that. Solar Pro Plus is fighting to keep their avionics from melting at 200 degrees. We have to keep a bunch of cryogens alive doing the same thing. So for sure, there are a lot of thermal challenges involved in that, particularly that last mission.